Hi, I hope everybody had a wonderful spring break. Well, as wonderful as it can be when you are in coronavirus quarantine. Um, because we had one day where we did not have class at all while we were trying to transition for the coronavirus, we are actually one section behind. So I'm going to, there'll be more videos than there were supposed to be on our syllabus. Um, and I'm still trying to decide if I'm going to do review sheet and kind of do it online the same way I'm doing these lectures, or if we're just going to do the Q&A. But don't forget Q&A during your class time every Monday and Wednesday. So go in through Collaborate Ultra in D2L, and we will be in there doing a live Q&A. Okay, so today, now I'm going to go out of order. So some of you are probably confused that this says 4.2. I like to do 4.2 first and then 4.1. So 4.2. Okay, so we are going to learn calculus backwards and forwards. You already learned it forwards. We learned how to take derivatives. Now we're going to go backwards and take antiderivatives. Okay, so we're going to start here talking about what the antiderivative gives us. So let's just start with this. Oops, sorry. Okay, this is a velocity function. Remember, a velocity function is a derivative. Okay, now this velocity function is a constant, saying our velocity is 50 miles an hour. And we travel that distance, or that velocity, sorry, for 2 hours. Okay, that means the total area, the total distance that I have gone is 50 miles an hour times the 2 hours, which gives me that I have traveled 100 miles. Okay, so that is the area under this curve. Okay, and in this case, obviously it is a rectangle, so it doesn't seem very curvy, but we still call that a curve. Oops, there we go. Okay, so let's suppose that it's something a little bit different, like this one. I'm going to move this someplace where it will be out of our way. Maybe back up in the corner over there. Okay, so the velocity of a moving object is given by this function. Okay, so this time it is not just a constant, it is a linear function. X is in hours, velocity is in miles per hour. So this time the shape is a triangle. Okay, so area of a triangle is 1/2 base times height. Okay, so let's try to get, we want to know the distance traveled during the first 3 hours. Okay, so during the first 3 hours, that's the area that they've got shaded right now. Okay, my base, let me rewrite that formula, base times height. The base is 3. So we've got 1/2 times 3. Okay, the height. Well, the height is right here. Okay, and this is the top of that triangle. You will notice that that is on our velocity line. So what is the x value that I could plug into my velocity formula that will give me what this y value is? Okay, so we are going to plug 3. The answer is 3. I know I wrote over the top of it, but that should be a 3 there. So I'm going to plug 3 into this formula. So 3 times 3 is 9. So my height is 9. So we get 1/2 of 3 times 9, which is 27. So that should be 13.5 miles. Okay, that one makes a nice triangle. Okay, the next one says between the 3rd hour and the 5th hour. Okay, so this time we are talking about this section over here. Okay, I want this section. Okay, so I want you to think for a minute about how I could get the area of that section that I drew in with the stripes. Okay, and there are a couple of ways to do that. The way that they show here is they broke it up into a rectangle and a triangle. So the rectangle, the width of the rectangle is 2. The height of the rectangle is defined right here, and we calculated that last time. That was 9 plus 1/2. The base of my triangle is 2. The height of the triangle, okay, so we have to go here. X value is 5, so my Y value is 3 times 5, which is 15. Okay, but 9 of that 15 went to the rectangle. So the triangle is only 6 units tall. Okay, so we have 2 times 9, which is 18, plus, well, 2 times 6 is 12, and half of that is 6. So the total is going to be 24. Okay, now some of you may have thought of a different way. And the way I initially thought of doing it, now if you liked the way we just did it, turn your brain off for a few minutes. If you thought about doing it a different way, what if, instead of doing what we just did, I said, okay, this part that I just outlined in purple makes one really big triangle. And if I just subtract out that triangle I already got, I'm left with this purple section that I wanted. Okay, so we know that the whole big triangle, so 1/2, the base is 5 units. The height, we already got, that's going to be 15. Okay, that's the whole big triangle. We don't want the whole triangle, but we do know we already calculated that this little triangle was 13.5. So we're just going to subtract that out. So 5 times 15, that is 75. Divide that by 2. So we have 37.5 minus 13.5. So big triangle minus the small triangle, which will give me 24 miles. So either way, you get 24 miles. Okay, what if it really is a curve and it doesn't break up into nice shape like those other ones? Okay, well, one thing that we could do is try to approximate it using rectangles. Okay, so we divide it up into rectangles of the same width. They will have different heights, but they are all the same width. And we try to approximate it. Okay, how do you feel about the job that those rectangles do in explaining that area? Does that feel like a good fit to you, or are you bothered by some of these pieces where we are not quite in the curve? Okay, so, and usually the answer is that you guys hate it because it really doesn't fit quite right. Okay, but the first thing we want to do, so if we're going to do rectangles, remember, length times width, or we'll call it height times width. Okay, so to get the width of the rectangle, we're going to get delta x. Okay, we're going to start at one number, end at another number. Okay, so B minus A, that's going to give me this distance. And then I'm going to divide it by the number of subintervals I want. Okay, they said 4 here because they were dividing in 4. This really is your more generic version. Your ending number minus your beginning number, and then divide that by how many rectangles you're going to want to divide it into. That's going to give us our width for each of these rectangles. Okay, so how are we going to get, and actually let's go back to that other page. How are we going to get the heights? Okay, so the height of each rectangle. Now, there's a number of ways you can do this, but you have to pick one, and you will be told which one to use. This is called left edge defined because it is defined by the left side of each rectangle. Okay? It could also be center defined, or it could be right edge defined, and then our heights would change. If this was right edge defined, this first rectangle would go all the way up here. Okay, but it doesn't. We're gonna go with left edge defined. What that means, how that's important to us is whatever this x value is for this rectangle, that's what I'm going to plug in to get my height. I'm going to plug in this x value to get the height of rectangle 1. I'm going to plug in this x value to get the height of rectangle 2. I'm going to plug in this x value to get the height of rectangle 3, and I'm going to plug in this x value to get the height of rectangle 4. Notice, we do not plug in this last value. Okay, that there's not another rectangle over here. All right, so that's how we get our heights. We're going to put in x values to find out what the y value is. Okay, so if we had the graph of 600x minus x squared over the interval from 0 to 600, we want to approximate the area by dividing it into 6 subintervals. Okay, so the first thing we want to do is divide that into 6 subintervals. All right, so this goes 600 minus 0. That was my B minus A, and they said divide it into 6 subintervals. So the width of each rectangle is 100. The width of each rectangle is 100. This one we're going to use left edge defined. So my heights are here. Those are the heights. Okay, so for my first one, I'm going to take, let's go back. I'll rewrite this for 600x minus x squared. Okay, this is the function. 600x minus x squared. Okay, that means that I need to plug, 0 in there. Okay, so I need f of 0. Now I would plug this 600x minus x squared into my calculator, and then I would just put these numbers into the table of values. F of 0, when I plug 0 into this, my answer is 0. 600 times 0 is 0, minus 0 squared, still 0. Okay, the next rectangle, so that was rectangle 1's height. The next rectangle is here. Okay, its left edge is at 100. Okay, we moved over 1 rectangle's width. So f of 100, I'm going to enter this into my y equals real quick so we can get all of these values. So 600x minus x squared Okay, and we have 100. So at 100, that was 50,000. Okay, now the next one, again, moves over another 100. So this time it's going to be f of 200. That's my x value, is 200. Okay, remember, this is specific to this example. They're not always going to move over by that much. Okay, so f of 200 is 80,000. The fourth rectangle, so that was rectangle 1, 2, 3. The fourth rectangle is at f of 300, which is 90,000. Okay, f of 400 gives me the height of my fifth rectangle, which is 80,000. And f of 500 gives me that last rectangle, which is 50,000 again. Okay, so now we have our heights. Okay, the area of each rectangle. Well, the area of each rectangle is the height. So rectangle 1. Rectangle 1 had a height of 0. Height of 0 times a width of 100. So rectangle 1 had an area of 0. Rectangle 2 had a height of 50,000 times a width of 100. Okay, so that is, I believe, 5 million. Okay, rectangle 3 had a height of 80,000 times a width of 100. So that was 8 million. Rectangle 4 had a height of 90,000 times 100. That's my width. So that is 9 million. Rectangle 5 had a height of 80,000. And we're going to multiply that by 100. That's my width. So that's 8 million. And rectangle 6 had a height of 50,000 times the width of 100, which is 5 million. Now, I need to add all the areas. So we're going to add those 6 areas together, and we should get, I believe it is 35 million. Yes, 35 million. That is our total area on this one. Okay, so we are just creating rectangles to fill in that space. Now, you probably are looking at that thinking that that does not give us a very good picture of what's actually going on. So what if we did this? Now, we are not going to do this example. We're not going to divide it into 12 and add all 12 together. But do you feel like this one gives a better estimate of what the area is than the one with 6? Okay, this one looks like this. The one with 6 looked like that. Yeah, it's a little better. What if I could draw even more rectangles? What if I divided each of these in half? So I had another rectangle here, and then so that was shaded in, And I had another rectangle here, so that's shaded in. Another one here, so that's shaded in. And again, these would go all the way to the bottom, right? I'm trying to divide those in half, okay? Would that, if I divided that into 24 rectangles, would that get closer to something that looks a little better? What if I could divide it into an infinite number of rectangles? And that is where we are going with the antiderivative. Okay, so the antiderivative, what we just did with all those rectangles was something called Riemann's sums. Riemann was the man who discovered this. So if we could make an infinite number of rectangles, so we would take the limit as x went to infinity, we would find that we would get the antiderivative. Okay, so I want to start with the antiderivative is going to be f of x. We're going to go from whatever our f of x is backwards to what the original problem was. But I want to give you guys some examples first. So let's look at this. If I take x squared, think about what the derivative of that is. Derivative of x squared is 2x. Okay, x squared plus 7. What's the derivative of that? 2x. X squared minus 100. The derivative of that is 2x. Okay, so remember, we're going backwards. We're starting now with this, and we want to go backwards. Okay, but if I start with 2x, all of those were 2x. How do I know which of these original functions that came from? Because I want to go back to the original function. Okay, the answer to that is we don't. So for right now, we're going to do something called the constant of integration. We're going to add c to whatever function we get, saying, I know that it's x squared. I don't know what's added to the end. I don't know if it's a plus 0, a plus 7, a minus 100, minus 25. I don't know. I know that there is some number out there, and I just don't know it. So on all of these, you need to add the plus c when you take the antiderivative. All right, so let's get to how to take an antiderivative. Okay, the first one is your constant function. So if I want to take the antiderivative of 5, okay, that means this is a derivative. I want to go backwards. Okay, how did I get to 5? Well, if I have something like this, 5x, the derivative of 5x is 5, right? So we're going backwards. So you'll notice that we give it a variable. Okay, do not always give it an x. Please pay attention to what the variable in your function is. It's not just automatically add an x. If our variable was t, then this would have been 5t. Okay, so we take this, we give it a variable. In this case, it is an x. So my antiderivative, or my derivative, my antiderivative is 5x plus c. All right, that's our first rule. This one, number 2, I like to call the reverse power rule. So I want to remind ourselves real quick, let's go over here. If we had x to the 4th, okay, in order to take the derivative, if I want to take a derivative of that, y prime, we would bring the 4 out in front, we have the x, and then we would subtract 1 from the exponent, right? So we multiply by the 4, then we subtract 1 from the exponent. To get the antiderivative, I'm going to go in reverse. So the last thing I did was subtract from the exponent. So we're going to do everything in the opposite order. So to get the antiderivative, oh, sorry. Ah, there we go. To get the antiderivative, we are going to add 1 to the exponent and then divide by that new exponent. Okay, so the antiderivative, we're going to add 1 to the exponent and then divide by that new exponent. Antiderivative of, let's say, x cubed dx is going to be add 1 to the exponent. So I'm going to have x to the 4th and then divide by that new exponent. And then, of course, we always have a plus c. Oh, I can't squish my plus c up there. X to the 4th over 4 plus c. That would be our final answer. Add 1 to the exponent, divide by the new exponent. Okay, that is our reverse power rule. Okay. Couple other rules. We're only going to learn 4 of them total. X to the negative 1. Now remember, we can write that as 1 over x. 1 over x. There was a derivative that we took of 1 over x. When we had 1 over x and we took the, when we had natural log of x and we took the derivative, we got 1 over x. So 1 over x, you just have to remember its antiderivative will be the natural log of x plus c. Okay, and also remember that that is only defined if x is a number greater than 0. I cannot take natural logs of negative numbers. Okay, so anytime I have 1 over x, the antiderivative is going to be the natural log of x plus c. And our last one, let's think about, before we do our last one, I want you to think about this. If I had 4e to the 4x, what would the derivative, if this was y, what would y prime be? Okay, y prime is, write it exactly as it appears, and then multiply by the derivative of the exponent, which was a 4. So we would get 16e to the 4x. Okay, that's its derivative. We wrote it as it appears, and then we multiplied by the derivative of the exponent. Remember, this is going backwards. So we're going to write it exactly as it appears, and then divide by the derivative of the exponent. So let's use the example I just did. We had 16e to the 4x. If I'm taking the antiderivative, I'm going to write it exactly as it appears. So 16e to the 4x, and then divide by the derivative of that exponent. So 16 divided by 4, so I'm going to get 4e to the 4x plus c. All right, here are a few examples. So let's go over those real quick. So on A, we have a constant. That's our first rule. So for a constant, and this time this dx tells us that our variable is x. So we have 8x plus c. Okay, antiderivative of 3x squared. Add 1 to your exponent, so I have x cubed. And then I divide by that new exponent. Okay, well, 3 over 3 is 1. So that simplifies down to x cubed plus c. Antiderivative of e to the x. Write it exactly as it appears. then divide by the derivative of the exponent, which was 1. So that is e to the x plus c. And part D, the antiderivative of 1 over x is ln x plus c. Okay, there are some more examples. If you pull up these notes in the notes section in D2L, you can do some more examples of those. I'm going to focus on just a couple of these. So I want to focus on this one, letter C. So on letter C, we want to rewrite this, let's see, I think it's here, as x to the 1/2. Okay, so we have the antiderivative of x to the 1/2 dx. Okay, now remember, we're going backwards, so we add 1 to the exponent. So x 1/2 plus 1 is 3/2, and then divide by that new exponent. Okay, you're going to have to remember some old algebra math laws. Dividing by a fraction is the same as multiplying by its reciprocal. Reciprocal means flip the fraction upside down. So we're going to multiply by 2/3 plus c. Okay, so that's how we're going to get the answer to that one. The other one wanted to look at is 1 over x cubed. I can't just use the natural log here because the natural log only works for 1 over x. This is 1 over x cubed. That's not going to work. So we need to be able to rewrite it like this. So antiderivative of x to the -3 dx. We add 1 to the exponent. So we get x to the -2. And then we divide by that new exponent. Okay, you can leave it like that, or you could even do -1/2 x. All right. Again, these are more that you can check on your own. Here's one with e to the x. So we have e. I want to take the antiderivative, write it exactly as it appears, and divide by the derivative of the exponent. Okay, divide by the derivative of the exponent. Okay, let's do a couple more of the e to the x. So we have, write it exactly as it appears. Derivative of the exponent is -3, so we're going to divide by that. Don't forget your plus c. Again, write it exactly as it appears. Derivative of the exponent is 1/2. We're going to divide by 1/2, which means multiply by the reciprocal. So we get 2e 1/2 x plus c. Okay, now some properties of anti-differentiation. Okay, if I have a constant sitting out in front, I can pull that constant out front, take the antiderivative of the function, and multiply them together at the end. These are the same rules that we've been using for derivatives as well. When I have two things, I don't know why my computer screen keeps doing that, but when I have two things added together, I can take the antiderivative of each one separately. Just like we do derivatives, we take the derivative of each one separately. We're going to do that same thing here. Okay, and let's try part A. So we have the antiderivative of 3x to the 5th plus 7x squared plus 8. We're going to take the antiderivative of each one of those separately. So we have 3x. Now we're going to take 5 and add 1, so we have 6. Divide by that new exponent. Plus, okay, now we have 7. x, add 1 to the exponent, so it's 3, and divide by 3, plus 8x, and then we're just going to put the constant once. Okay, we don't need to write it 3 times. We'll just add all those different c's together. They make one big c at the end, okay? This can be simplified, so we're going to rewrite this as 1/2 x to the 6 plus 7 thirds x cubed plus 8x plus c. All right, and the next one, we want to rewrite that as separate fractions. So see how they separated them into different fractions, and then they were able to simplify each one. Okay, so we're going to take the antiderivative of 4 over x. Okay, so on this one, antiderivative of 4 over x. Well, that's like 4 times the antiderivative of 1 over x. And the antiderivative of 1 over x is the natural log of x. So this will be 4 ln x. Okay, the next part, we have 3. Antiderivative of 3 is going to be 3x. And then finally, the antiderivative of 2x cubed. Okay, we're going to write 2x. Now, I add 1, so instead of a 3, it becomes a 4. Divide by that new exponent. And then that, of course, simplifies to 1/2 x to the 4th. Now, I'm going to put all of those back together, and we're going to use the same signs that they started with. We had pluses. So we have 4 ln x plus 3x plus 1/2 x to the 4th plus c. Okay, there's some more for you to practice. Remember if you had something like this, you would have to multiply it out first. We do not have a reverse chain rule. And these, again, you're going to want to simplify those because we do not have a reverse quotient rule. Okay, so the answers for those should be in your the other notes that I have posted will show you the answers to those as well if you want to give those a try and then check your answers on those notes. Okay, if you have any questions after that, then let's talk about those at one of those Monday or Wednesday Q&A sessions. Okay, the last thing we need to do is they are giving us something called an initial condition. Okay, so when you have an initial condition, first we're going to get the antiderivative. So we have the antiderivative of x squared. We'll add 1, so it becomes a 3 divided by a new exponent. So I get x cubed over 3 plus c, right? That's our antiderivative. We just learned how to do that. Okay, this initial condition means when x is -1, the answer to this problem is a 2. Okay, so when I plug -1 in, so I have -1 cubed divided by 3 plus c equals 2. We are going to solve for the c that makes this true. So we have -1 cubed is still -1, so I have -1/3 plus c equals 2. I'm going to add 1/3 to both sides. So before I do that, I want to change 2 into thirds. So 2 is 6/3. Add 1/3 to both sides. So I get that c is 7/3. Okay, we have solved for the specific c that works in our problem. Okay, so for our specific example, our f of x is going to be x cubed over 3. And instead of putting plus c at the end, I'm going to finish it out by adding our specific constant at the end. Okay, so that is how we solve for C when we are given an initial condition. Given an initial condition, take your antiderivative first, and then plug whatever the x value is into the function to see what your y value will be.